Hello guys, today we're going to go over 0.4 nth roots and real exponents. Now let's go over a couple of basic facts. Remember that the nth root n can either be even or odd, and at the same time the value a can be positive or negative. Now a couple of different things happen when n is even or odd and a is positive, negative, or zero. So let's look at each scenario. First of all, let's focus on n is even. If n is even and a, for example, 2 square root, and a is a number bigger than 0, say 4, you're going to have two real answers, a positive and a negative 2. So square root of 4 is positive, negative 2. If n is odd and a is 0, you're going to have one real answer, 0. And if n is even and a is negative, remember we factor out the negative 1 or the square root of negative 1, turn it into an imaginary, and pretty much your answer will be an imaginary solution, or two imaginary solutions, no real solution. So when n is even and a is positive, two real solutions. When n is even and a is 0, one real solution. When n is even and a is negative, no real solutions. Pretty much like the discriminant for the quadratic formula. By evaluating the discriminant, you can easily tell two real, one real, no real. Same thing applies here. Now note, when n is odd, when n is odd, it's different. Because say, for example, I have cubic root of negative 8. We can actually reach the cubic root of negative 8. It's negative 2 cubed. Negative 2 times negative 2 is positive 4 times negative 2, negative 8. So when n is odd and when n is odd and a is greater than 0, you have one positive and 0 negative roots. So for example, cubic root of 8, it's just going to be 2. So when n is odd and a is positive, pretty much one real solution. When n is odd and a is 0, same thing, one real solution, 0. And when n is odd and a is a negative number, again, one real solution. Pretty much, negative root. So just one real negative root. That's it for the intro. Now let's focus on the actual examples given in the book. Let's go over example A. Find the nth root. Now note that this negative, in the first example, example 1A, this negative is outside of the root. So pretty much you just do normal operations following PEMDAS. The square root of 49 is positive negative 7, but then you apply the negative and pretty much the answer is negative 7. Looking at example B, it's slightly more complex. I have cubic root of 64 over 27. Now remember, when you have a division, you can just pretty much break up the cube roots into numerator and into denominator, and then do each operation separately. So the cube root of 64 is 4. 4 times 4, 16 times 4, 64. And the cubic root of 27 is 3. 3 times 3, 9 times 3, 27. And, just in general, the process also works backwards. If you ever want to do it, just to simplify or to join radicals, numerators, and denominators, you can definitely do that as long as the nth root is the same, okay? So that is example B. Let's go over example C. Now I have fourth root of negative 121. Now remember, you factor out the negative 1, turn it into I, and then you just proceed to work. Or you can just say that, it's a negative number, so that's pretty much it. Now, let's continue. A key concept we see in the following page is pretty much the following. If you have two roots, so the same nth root, for example, square root of 4 and square root of 16, if you ever want to multiply these, again, you put the same power of the roots and then you just multiply these numbers. You can join them or also break them apart. For example, square root of 40, you can break it up into square root of 4 and square root of 10. The square root of 4 is positive -2. And then you can just simplify the 40. So again, you can break numbers however you pretty much want. And for example, the square root of 32. You can just do square root of 2 times square root of 16. Square root of 16 is positive -4. And there you go. You can pretty much easily simplify roots by breaking them down into factors and then doing the square root of the factors if the original number doesn't have a perfect root. So again, you can just break them up and then do the square roots as needed. Let's go over example A. Now example A, there's a couple of ways to do this. I teach it slightly different. That's in the book. I think it's just easier, but we're gonna go over both ways. So they give me 6 root of n to the 18. Now, the way the book works is it tries to equal an exponent here and the power of the root to just cancel them out. And that's a good way to work. Again, knowing the rules of the powers and exponents, you can say that this is identical to n cubed elevated to the 6th power. Because again, power of a power you multiply. When you multiply these two, you end up with 18. But now, 18 is the same thing as this, only now the 6th root and the 6th power, they cancel each other out and you're left with n cubed. Now, I don't like it this way because when you're given multiple variables and multiple values, it gets kind of tricky sometimes. The way I do it is, you can think of this as a toll. You gotta pay 6 to exit the toll booth or the lane. And this guy has $18. Pretty much, if he has $18 and it costs 6 to exit the toll booth, how many cars can pass? Pretty much 3 cars, and you're left with zero. You're left with $0. $0. You leave whatever's left over inside and whatever can exit. So for example, if this was n to the 20th power, yeah, 3 guys can pass the toll, or 3 cars can pass the toll, and you're left with $2. Pretty much, I just find this way a lot simpler, and it works with however many variables you have. For example, let's say I have square root of 63 and y to the 3rd power. Now, I taught you guys to do the little breakdown of the factors when you can't just normally break them up. So 63, to do the little breakdown tree, you can't divide it by 2, but you can definitely divide it by 3. When you divide 63 by 3, you end up with 21. Now 21, again, can be divided by 3, and you're left with 7. 7 can only be divided by 7, and you're left with 1. When you're left with 1, you just stop working right there, and whatever's on the left-hand side becomes your factors with the proper exponents. So again, this 63 is the same thing as 3 squared times 7, and then I have y3. No, that's a multiplication as well. After you simplify the number into actual factors and exponents, now you can just do the toll trick. Okay, here, this guy can pay, because remember, when we don't see the number, it's 2 squared. This guy can pay, so he exits. The 7 can't pay, so he's left behind. Y has $3, it costs 2, so 1 Y can exit, and I'm left with 1 Y that was, $1, pretty much. He wasn't able to go through the toll, so he stays behind. That's how I'd rather do it, and that is example C. Example 4 is pretty much similar. Again, the book explains it differently, but I'd rather do it my way. I just think it's way simpler. I have quartic root, or 4th root of 81, and then a plus 1 to the 12th power. Note that this is inside parentheses, so this counts as a single term, like a single variable. So again, the 81, I can't divide it by 2, but I can definitely divide it by 3. When you divide by 3, the answer is 27. 27 times 3 is 81. This can be divided by 3, 9. The 9 can be divided by 3, 3. And the 3 can be divided by 3, 1. So pretty much 81 is the exact same thing as 3 to the 4th power. And I also have a plus 1 to the 12th power. And now I do the toll trick. It costs $4 to cross the toll. This guy has $4, so he goes through. There aren't any dollars left. And this guy has $12, so 3 of them go through pretty much. And you are done. That's pretty much it. Let's continue. Okay. Now we get into the tricky part we saw last year, converting radicals to rational exponents. Now when you have, for example, this expression, you can turn that into a base where the power of the root becomes the denominator and the exponent that's out here becomes the numerator. Since I can't see anything right now, the exponent is 1. So it would be a to the 1 over n. So for example, if I had 3 to the 6th power, I put the same base, the root becomes my denominator, and the exponent here becomes my numerator. If I don't have anything, it would be 1. Let's give you guys one with, say, for example, an exponent. Say I have cube root of 80 to the 3rd power. This would be the exact same, well, not 3rd power, because again, this would just cancel this out. To the 4th power, it would just be 80. The root becomes the denominator, the exponent becomes the numerator. And that's how you switch. And you'll see why that's important right now. And again, it goes vice versa. Let's say, for example, I have 17 to the 5 over 6. You put the 17 in a root, the 6 becomes the power of the root, and the 5 becomes an exponent. Now, that exponent can be, inside or outside, but it's pretty much the same thing. I like to put it on the outside, just makes it easier. Now let's go over example 3a. It's a little tricky, but again, step by step, you'll be able to manage. I have 32 to the 10th power over 6 root of 2. Now, when you see these types of problems, you're going to have to try to simplify the numbers as much as possible. And you can use the little tree I just showed you guys. And you already know from 9th and 10th grade. So 32, I can divide it by 2, it becomes 16. I can divide that by 2, it becomes 8. I can divide that by 2, it becomes 4. Divide this by 2, it becomes 2. Divide this by 2, becomes 1. And I'm done. So all these 2's, you just switch it for the number. So this is actually 10th root of 2, 1, 2, 3, 4, 5 to the 5th power. Remember, the exponent can either be inside or outside. That's absolutely fine. And my denominator stays identical, 6 root of 2. And again, I hope you remember your 10th grade. Remember, I warned you guys, the rules of the powers and exponents, they're going to be used a lot. So you better review them. When I turn this into a rational exponent, remember, the base is the same. The power of the root becomes my denominator, and the exponent becomes my numerator. And the same thing down here, 6 to the 1st, and the 1 down here because there is no exponent. I simplify this into 1/2. Now, remember what happens here. You can send any number from the denominator to the numerator, and all you gotta do is change the sign of the exponent. We saw that last year. Again, a small example. If you have x cubed and x squared, visually, you can just simplify. I take 2 away from here, I take 2 away from here, and I'm left with x. But what's actually happening is this variable gets sent up here with a negative exponent, and you just subtract it, and 3 minus 2 is 1. So the same concept applies here. I have 2 1/2, and I'm going to send this up here with the exponent changed. And remember, when you multiply two same base, like variables or terms, all you gotta do is add the exponent. So this actually becomes 2 to the 1/2 minus 1/6. When you do that actual process, you're left with 2 to the 1/3, or if you want to change it into root form, cubic root of 2, and you're done. They are both identical. They are both correct. So you can do whichever one you choose. Let's go over the last example. Again, 4th root of x to the 21, y to the 15. Now, if you note, the book does a whole bunch of operations or process just to clear this up. Again, you can just do the whole total thing. 5 of them go out, and you're left with $1. Oh, also try to leave some room for the rest of the vehicles that are going to come through. This guy can pay 3 tolls, and you're left with $3. Again, this guy paid 5 tolls, 20, was left with $1. This guy paid 3 tolls, 12, was left with $3. That's the answer. Just pretty simple and straightforward. That's it for today. I will see you tomorrow. Take care.